Hey guys, welcome to my video on optimization and implementing a solver in Simulink. If you are somebody interested in autonomous self-driving cars, a model, predictive control, machine learning, AI, financial modeling, and these kind of topics, then optimization is a very important concept to know and understand because most of machine learning is actually this. It's used all the time for NPC and also for self-driving cars. So optimization is essentially finding the best solution for a problem. You have something that you want to optimize based on some constraints, which are limitations, and you have the variables which you need to be optimized for. You use all this to make a cost function, and then you have two solutions, an unconstrained solution and a constrained solution. In this video, we'll be looking at quadratic optimization. This is commonly used in machine learning a lot, along with AI and NPC. This will be focused for NPC or model predictive control. You have a quadratic function with linear constraints, and they can be represented like this. So you want to optimize the variable x, that is a vector of things that you want to solve for, subject to the constraints there, f and g, and your cost function is given like so. Here's a little picture of optimization in NPC, an example of a cost function that's used in NPC. And you will see this more in detail when I do the Simulink example. So we look at the solvers now. So you have to activate a solver if your unconstrained solution does not meet the constraints, because you have to make sure that the constraints are always met, because in a real life system, for example, a car or something, you have limitations you cannot exceed. For example, you cannot like turn the steering angle too much, because then that's not good for the vehicle. So this needs to be taken into account, and this is how you activate a solver. We'll be looking at the PQP algorithm. This was invented at Mitsubishi Electric Research Labs, or MERL. This is a very high performance R&D facility in the USA, which does a lot of work in autonomy, controls, and so on. So now let's begin the Simulink example. So this paper I had the opportunity to publish during my master's degree at Concordia. It talks about NPC and optimization. I will directly skip to the optimization section because for the NPC that'll be covered in a different video. So whenever you optimize something, you have to use a cost function. You have to develop this yourself, and you also need constraints, right? Because the whole point of optimization is mostly when you have a constraint on something, want to make sure that it does not exceed that value. So in this case, we have input constraints. The inputs are between minimum and maximum, and also on the delta input, so delta u and delta u max, which is between each time step. So from equations 9 and 12, you have to use something called the duality principle to get these equations here, 13 to 15. You have to differentiate the cost function with respect to the optimization variable. So in this case, u is the optimization variable and lambda is the Lagrange multiplier. So this is very common principles in optimization. You have the variable and the multiplier, and you have to solve for the optimal values. So this takes into account the constraints, and for our optimization algorithm, you have to define two terms, w and z. Now w and z can be defined before, so they are based on your system model, which I will get into more details in the future. So for now, just make sure that you have w and z along with m and gamma here. So these terms have to be defined before. When you have those, you can proceed with the optimization. So then you have to use a solver. Now in MATLAB, you have many solvers which are built in. I believe if you have the MPC toolbox or any control system toolbox, they contain solvers for optimization. However, for now, we'll be doing it from scratch because it's a good way to learn. And this is a linear method, it's not a non-linear method. So for linear methods, it is quite simple to do it yourself. The solver which we'll be using is the parallel quadratic programming algorithm. This was designed at MERL. It's called Mitsubishi Electric Research Labs. This is a very nice research facility in the US, and they do a lot of work in controls and optimization, machine learning all those things. So this is the parallel quadratic programming algorithm here. I took it from the paper and I put it in this format so it looked nicer, and then you can see how it looks like here. So this max operator is taken element wise. I'll get into more of the solver when I show you the model, but for now, just take a note of this algorithm here. You have to start off with W and Z along with some initial conditions, and then you have to go through this loop and solve for the optimal Lagrange multiplier. So that'll be lambda star. And when you get lambda star, you return that. And from this lambda star, you can then solve for U star. So you take equation 14 and you put in this lambda star there, and that gives you the optimal inputs. And I will demonstrate that and it'll make a lot more sense to you. So let's begin. So when you download the files from GitHub, you will see them like this. First thing you want to do is you want to navigate to the folder. So in my case, it is in here, and open the PRJ file. So that should load these two files here. The first thing you want to do is you want to load the inputs into the workspace. So open up userinputs.m and you will see it there. So essentially, I have some parameters already defined here. H inverse is from the paper. I just took a value here. So in this case, I have a couple of inputs, two inputs. My constraints are that the first input is bounded between 0.4 and negative 0.4, and the second input is bounded between negative 0.15 and 1. So those are my constraints, and M is just a mapping matrix. Initially, I don't have any incremental constraints, so I just set this to 0. I will get more into this after. So yeah, now I have my quadratic program parameters for the PQP algorithm. You know how I mentioned you need W and Z. So in this case, I have my W. It is a function of M, H inverse, and M transpose. I can already solve for WM and WP beforehand because I know what W is, right? So I can save time and just solve it now itself. A QP is a struct, so qp.w.wm belongs to the QP struct variable. I have my qp -.l underscore 0 line 26. That is my initial Lagrange multiplier. So it has to be something which is more than 0. It's 0.1. It's a vector of 4, 0.1. My initial error should be more than 0 because you want the error to be small, but it'll only activate the solver if the error is high, right? So you want it to be initially a high value and then it'll go down. And this is just a couple of more structs I have to define the initial Lagrange multiplier. For now, my f variable is this. It is actually based on the control system error. I don't have my control system design now, it is just my optimizer, so I defined f there. And I have my unconstrained inputs. So let's run this file first and let's see what we get in the workspace. So it's loaded in the workspace. You can see the structs here. If I just type in QP, you can see how it's a struct. It contains W, WM, WP, the initial multiplier and the error, and then same with constraints. So it is a struct. Alright, so let's open the model now and let me explain how that works. This is my Simulink model. The first thing you want to do is press spacebar to make it fit the window. So this is my unconstrained inputs, and what this will do is this will check that the inputs satisfy the constraints. If the unconstrained inputs meet the constraints, it'll not activate the optimization. It'll just pass through this here. However, if it does not meet the constraints, which is in this example, it'll activate my optimizer. So this is a subsystem. If you do Control M on this, you can see that I went into a mask. So that's why it looks like that. It looks a lot nicer this way. So if I open this one up, I can see my optimizer here. Let's first look at the solver. Since I'm using a discrete time simulation, my solver will be discrete. It'll at a fixed time step of 0.01 seconds. And I will only do one time step. So my ending time will be the time step, which is 0.01 seconds, right? So And that is because my model will be done in discrete time, not continuous time. So all you have to do is make it very simple for the Simulink solver to recognize that. So there you go, make sure it is fixed step. Your step size is 0.01 seconds and it is discrete. Alright, so with that being said, over here I have my optimizer. I have my constraints there, M and G. So that's gamma from the paper. I use a bus selector to select M. So if I open this one, you can see how it is a bus selector block, and then I just select M and G0 there. And then I use MU. So I check that. I just multiply M by U, right? And then I use format G0. So this one here is a variant subsystem, because I may use incremental constraints or I may not. And in this case I don't. But I did it this way because if I do it after some time, it'll just activate this one. So now I will explain how variant subsystems work. So right click on this and select block parameters. You can see how it's a variant subsystem. I have two inside, append or no append. And this is my variant control. So it'll activate either of these based on the value of G underscore init. Press OK and then let's open it now. So you can see how I have two inside here. I have G0 and G. You have to make sure that inside your subsystem here, the inputs and the outputs have the same name. So here, input is G0, output is G. In the first one, the input is G0 and the output is G. And in the second one, it's the same thing. This one, what it'll do is, it'll activate the model if I have incremental inputs, but now I don't, so it'll not activate this. But I can just explain this very quickly now. So what this will do is, it'll do a U minus U at the time step beforehand. So it'll be UK minus 1, right? So this will select the top and the bottom. It'll just concatenate the array. So for this one, I use the selector block to select the last 4 elements of G. If it is an 8x1 vector, so 5 to 8, it's a size 8 inputs in this specific example. My assignment block, I just assign it there. So I just add it and then assign it. If you see the picture which I put up, then you will understand better. But for this case, I don't use it, right? Because it's just there in case I need it. So it'll just pass through this one here. So it'll just, So it'll just assign the output to the input. So that's what we use now. This will just compare MU and G. So this compares the constraints. And this sum value will just sum up all the values. Now, if the sum value is more than 0, that means you do not satisfy the constraints, and that is a Boolean. So you just put it here. That's your condition, right? So you want this to be 0 to not activate my solver. This here is the optimization. So this is where all the magic is done. You can see if I open it, I have, let's start off with the inputs. So I extract G and then put it into my optimizer. I have my inputs there. So that's all my W and Zs and all that. So W is here, WM, my initial multiplier, my error. I made a bus object. If I just click on this one, you can see how it is done this way. I have my signal names. I make it into a bus called PQP underscore in. This one is also a bus creator. And then I just select. I do M times H inverse times F. F is from the workspace, so I just use a constant to pull the value inside. I just select M, H inverse and G there. So I just select it this way. Once that's done, I actually form up Z in here. I solve for Z, ZP and ZM because we need this in the optimizer. So Z is over here, right? So it is M H inverse times F plus G. If you see in the paper, I form up ZP. So this is basically a max operator. So for this one, this is a subsystem. So if I click on this one and if I open it, so this will take the width of Z, and that is how many for loops you have to do, because in this case z is a 4x1 vector, so you will have n equals 4. When I compile the system, you will see this value change. And for this one, I select each value of z and I check it. So here, it's selector, I'm selecting each value of z. It is a 4 vector, so I just put 4 in there. And then I compare it to 0, right? This is a switch operator, I'm comparing it. So if it is more than or equal to 0, then it'll pass through input 1. Otherwise, it'll pass through 0 here. So it'll just reassign values of z. This is my assignment block. So for this one, all you do is you put this into a port, index vector port, select this option here. Output dimensions 1, that's good. And then initialize it this way. So you just assign the values of z here back, and you will get zp, and for zm, you just put a -1 there. So you solve for w and z, and then you put it into the optimization loop. Inside my loop, I select the error. So this is a while loop and a for loop is inside the while loop. So I make sure that my initial condition is that the error is more than 0, which it is. It'll only activate when this is equal to a boolean 1. So if I enter the subsystem here, but if I actually first go back and if I right click on this one and if I select subsystem, it is just a normal subsystem, and inside here I have a while iterator. So you have to drag in a while iterator browser, if you can see here. Just drag in a while here, so which is this one here. You just drag and drop it inside and then do all the connections there. And inside this while loop, I make sure that I have a for inside here. So for this one, it is again in the library browser. It is the for iterator subsystem, so that's this one here. You just drag and drop it. But first, let's explain this while thing. So the condition is that you want the error to be less than 0 or some value close to 0, which is 0.1 times 10 to the power of -5. So it'll stop there. So while this condition is not false, it'll just keep on going. And the moment you do not meet this condition, it'll stop the loop. So inside here, I do have a maximum number of iterations. So this could be -1, but then you may have an infinite loop, but you don't want that. So in most cases, you have to have the optimizer converge. You don't want it to fail. So I just put 700 for now. I do have I do this, so make sure you click that to select the iteration number port, and I will show you why after, and leave everything else as is. So that's my parameters for that. Now this is where my loop is done. So initially at the first iteration, I have my initial Lagrange multiplier, so you have to pass in this one here. So the iterations come out of this and they go into this comparison. So only for the first iteration you have to pass in this lambda, but then after that you will have to use the loop. So when iterations becomes more than 1, it'll pass in the top input, which comes out of my for loop. So now let's go into for block and let's explain this one. So in here I do my for loop. So in this case, I have a similar structure. I have my for block in here. For this one, make sure your iteration limit source is external, because you have to pass in the dimensions from there. And then you click show iteration variable there. So what this will do is it'll take in the dimension of z, and that'll be your iterations maximum. So this will be 4 for this case. You solve for Wm and Wp based on your optimizer, how the structure works. So you get all these parameters, and then you solve for your Lagrange multiplier. You have to update your lambda, but you have to update lambda each element of it. So that is why this index here I is from 1 to n, right? So yeah, let's go into this one and let's see how that works. So I pass in my I, so I equals 1, 2, 3, 4, and you pass it in the index here. make sure the index vector is port because you have to pass it from the outside. Don't select dialog, make sure it's port. The input port size will be 4 because you have a 4 element vector here. And when that's done, you have to simply calculate lambda I in this case. So you just pass in I all the way down and you use km, zm, kp, zp, and then lambda old. So based on the formula, you can see it's quite straightforward. You just update lambda I. The most important thing to know is that you have to pass in the iteration from I equals 1 to 4 outside. So that is why I mentioned to select this as a port because it has to be passed in. So don't forget that. And then when you have lambda I, you have to update lambda, right? So that is done via this assignment block here. So in this case here, I have, once again, it is a port. Make sure it is all ports, okay? So yeah, I have my initialize output with this one. So what this one do is that is my original output. That is my input. So it'll assign u to y0, okay? So that is why my updated lambda goes into u. That's your update and that is your old value. You can see how the old value is simply lambda old. It's being passed into y0. And then you will get y, right? So I hope you understood this very well. So I have my lambda in here. I also output my lambda old because I want to solve for the error. So I pass in lambda back inside because I needed to update that at each iteration. So you have to pass it in this way. And now pay very close attention because this here is the deal breaker. I spent like 6 hours trying to figure this out and I was missing this unit delay block. If you don't have this, you will cause a lot of issues. So make sure you have it, please, especially when you update the same variable again, because I spent like all this time trying to understand why my thing wasn't working, but I finally got it to work like after I put this 1 over z in. So this unit delay block, make sure that the initial condition is lambda old and then the sample time is -1, okay? So that's very crucial. If you look at the Simulink documentation for unit delay blocks, you will understand what I mean. So I'm just gonna quickly open that here and then I will show you. So look, so if you read this carefully, you will see what I'm trying to explain to you. So there we go. If it is an iterated subsystem, it'll hold and delay the input by 1 iteration. So this is very important to know. And that is why I have it there. So with that being said, you can solve for the error. So this is simply lambda minus lambda old. That is my delta lambda transpose times delta lambda. So this is a simple multiplication. And then I will pass the error into here. I check that the error is less than 1 to the power of -6. If that is true, this iteration will stop. You can also output the iterations and the error like so in this XY graph there. So when I have my optimal Lagrange multiplier, which is the output of this while loop and for loop inside it, I can then solve for my optimal inputs. So this one is quite straightforward. You just simply do some basic math here. So just do transpose times multiply times 0.5. You have to reshape this into a 4 by 1. So you have to make it a column vector because it is a column vector. So you will need this block here. It's called a reshape. And then you just add it to F and then you multiply it once again and then you get your optimal inputs there. So that's it for the program, and then let's see how it works. So let's run this model and see what we get. So if I go on, first you can do Control D to just update the blocks. And you will see how you will get the signal dimensions there. So that's very useful. If I just press run now, you will see the output. So this XY graph is the optimizer. You can see how the error goes to 0 eventually. Ignore this line here, this one here, because it's just a bug. But it starts off at 1, it goes all the way up to about 200, but then it'll come back down very fast. and then it eventually goes to 0. You can see how it solves for my inputs. So here is my unconstrained input. The bottom one does not meet the constraints because it is less than negative 0.15. But if I optimize this whole thing, it'll give you the constrained input. So it capped at 1, which is the maximum value, and then 0.44. So this means that the optimizer does a good job of solving for these inputs. If I look at the scope, this scope here shows you the number of iterations which I used. It is about 700 if I auto scale this. So you can see how it's about 690. So it took that many iterations for the optimizer to converge. So with that being said, this program works and it works well.